Hey everybody, Mr. Fortin here with your optional video where I'm going to go through the proof of the IAT, the proof of the inscribed angle theorem. Now you're watching this video because you're really interested in geometry, you think you might be a math major, you want to see a complicated proof, or you just kind of thirst, right? You thirst for just wanting to figure out how things work and how things come together, and you want to see how this gets proven. So thank you for joining me here. Again, it's an optional video, or you're just watching this video just because you're sick like me, right? You're just totally just got this disgusting way of approaching things where it's just I want to get down and dirty with this stuff here. So anyways, we're going to go through the proof of this here. It's the longest proof I've written for this course, at least. And I need some help to figure out all the exact steps and figuring out the logic of where the book's going through. But anyways, I wanted to show it to you because this is a theorem, right, after all. And with a theorem, you got to ask, well, where's the proof? How do I know for sure? How is this building upon facts, rules, and definitions to establish this? That whenever I have an inscribed angle, okay, remember inscribed angle, two chords, common vertex of those two chords is going to be on the circle themselves. That's what an inscribed angle is. And it's equal to half the measure of its intercepted arc, okay? So then at the ends of the angle, right, with the two sides hitting the other parts of the circle in between the two sides, that's the intercepted arc. So anyways, let's get into this, and you'll see very quickly why this proof is going to be so long. And so, well, maybe not complicated, but at least so long. You can just say that right away here, okay? So here, we're going to prove this for a generic kind of circle. Well, any circle is kind of generic, right? There are no sides or anything like that. A generic radius here. But anyways, a circle here is circle O, and we can actually say that angles that are inscribed angles, we can say that that angle is inscribed in the circle here, okay? So we're given angle ABC, and it's inscribed in circle O. Now, it actually turns out there are three ways that are going to be necessary for us to prove, because we want to prove this for all inscribed angles, So this proof here, right, angle ABC is inscribed in circle O. Obviously, we want to get this so that measure of angle ABC, we want to show it conclusively, it has to equal exactly half its intercepted arc. We're going to actually have to talk about three particular cases here, okay, because it turns out the way that we're going to need to prove this is that we're going to prove this for certain types, or a certain type at least, a certain type of inscribed angle, and that's going to be case one. And then once we prove that this particular situation here, which I'll talk about in a second, is true, that measure of angle ABC, look at the way it's drawn right here, measure of angle ABC has to equal half the measurement of arc AC in this situation. We're going to use the thing we prove in case one, for case one, and then we're going to use that in case two. We're also going to use it in case three here. And then these three situations summarize any way you can draw an inscribed angle, okay? So see what I'm talking about real quick here before we actually jump into the proof. Case one, we're going to prove. So we're basically writing three proofs, right? The first proof, we're going to use what we proved in the first proof in the second proof and also in the third proof. But anyways, we got to write what appear to you as three proofs, right? We're going to start from square one each time, okay? The reason is because case one is actually an easier case to prove than the other two. And it's actually a necessary thing to prove in order to prove the other two cases here for any inscribed angles. Because inscribed angles, they could do this. And yes, this is the way that's easiest to prove right here, because it's going to connect to some other geometry stuff we studied this year. And that is if we have, remember, an inscribed angle, the vertex of the inscribed angle is on the circle, and the two sides are both chords. So it's possible a chord could also be a diameter. Yes. A diameter is a chord after all, right? A chord that passes through the center. So sure, this is a situation where one of the chords is a diameter, and it's actually pretty freaking easy to prove that measure of angle ABC has to be 1/2 arc AC. We're going to have to introduce an auxiliary line there, but once we get it, maybe you'll see it. Maybe you can help me with that proof here. Although it can be kind of hard to see right away. Yeah, we'll see it when we get to it in a second, okay? So once we have that, we're then going to do case two where, well, not all inscribed angles pass through the center of the circle, right? Not all inscribed angles, one of the sides doesn't pass through the center of the circle. So you really have two situations that we're going to need to prove on top of this, where we're going to use what we prove in case one, okay? We're actually going to draw an auxiliary set in here, right? Well, we'll draw another segment, another chord here that does pass through the middle, and then we're going to use what we proved for that side and that side here. So anyways, the second case is we're going to prove for an inscribed angle, because, an inscribed angle here, okay, wouldn't the center would be in the interior of the angle, okay, in the interior of the angle. So if the center isn't actually on the angle itself, it's either going to be in the interior of the angle, or in case 3, what we'll prove is going to be if the center actually isn't in the interior of the angle here. Here, this is another situation which we'll need a unique proof for, because it's a different justification. It'll use case 1 in this here. We'll actually draw a little segment, another chord, through the diameter here, and then we'll do like some subtraction here. Okay, so I think you'll see that one after we do case 2. You'll see what I'm talking about here. Without further ado, let's go ahead and get into it. Yeah, let's get down and dirty with this. Proving time. Yes, let's do it. When one chord is a diameter. This is case 1. This is the only diagram we're thinking about for now. So remember this theorem that any inscribed angle measures 1/2 its intercepted arc. That's true for any inscribed angle. We want to write the theorem for the most general, right? As general as possible. We can, but we need to prove something more specific. So what we're actually doing right now in case 1 is just proving that an inscribed angle that passes, where one of the sides passes through the center of the circle, equals 1/2 the measure of its intercepted arc, okay? And that's much more specific than the actual theorem. We want to broaden that with cases 2, cases 3, okay? You'll see it when we get there, but now we're just doing it with the diameter case right here. Okay, step 1. So I said this one isn't super hard to prove, and you might be wondering, well, where do I begin, right? Where do I begin? It's hard to get started in the actual proof. So that's where, somebody sat for a while, somebody took a while to figure out, well, I'm observing this, right? Early Greeks are observing this, that this angle measurement just appears to be like half of this. They thought, why? Well, then maybe the idea with this proof is maybe there's an auxiliary set you thought of, okay? You thought of. Well, quick hint here, how does an arc measure work? What measures the arc? Does the inscribed angle measure the arc? No, it doesn't. It's half, right? So we're going to prove it's half. We're going to do it in a second. What measures the arc? The central angle measures arc AC. So you know what? The first step of this is actually to draw in that auxiliary set, okay? I'm going to draw in segment OA, therefore creating central angle 1, okay? That's certainly going to be used in this proof. Again, measure of angle ABC, 1/2 of arc AC, okay? This equals measure of arc AC, angle 1 right here, because that's how arc measures get measured. Wait, how are these really? Wait. Look at some. Oh, I got a triangle up top there. You see it? See how we can do this here? I think actually a couple people would figure out how to prove this at this point here. Okay, so we'll draw radius segment OA. Okay, really we're just drawing segment OA through those 2 points. Okay, through 2 points, exactly 1 line can be drawn. Adding that auxiliary line segment through those 2 points that are there, totally valid. You can do it there too. So adding that auxiliary line. Step 2. Okay, step 2 is this. I want to start comparing angle 1 actually. So let's not worry about the arc yet, right? Angle 1 relates to this arc here because measure of angle 1 equals measure of arc AC, because the central angle measures its intercepted arc. But here, angle 1 is also actually related to measure of angle ABC. And we might as well say something about that right now, because if we can compare measure of angle ABC to angle 1, then right, kind of through transitivity or substitution or whatever, we can compare it to this arc, right? That would be our goal. So first step of this is to actually, well, before I do that, actually, when we draw in radii, we can take advantage of this. This is going to help us think what we have on the top too. It's just, I don't know if I do this in the perfect order, I guess. OA, what do we just drew in? I drew in radius OA. Was there already a radius in this diagram? Yeah, there certainly was. Right up here, right there. Congruent to one another. Those are certainly congruent because they're both radii. All radii in a circle are congruent to one another, and that's my reason there for number 2. I could have said definition of circle, right? Circle is defined as the set of all points equidistant from a fixed point. So radiuses are congruent to one another. That's what it's all about. Okay, so those are congruent. How does that help us? Well, step 3, what I was trying to get to earlier here is that, well, if actually, maybe I don't know what I did in step 3. If these are congruent here, that segment's congruent to that segment, I can actually make a conclusion about angle B that might help us. Remember, we're trying to talk about angle B ultimately. This measure of angle ABC is equal to 1/2 of the measure of arc AC. So I can say something about measure of angle ABC it's got to actually equal another angle in this diagram here. What angle is that? Let's see if I do that next. I don't do that next, do I? No, I do. Yeah, I do. I do put that in there. So I'll call it angle B in this one. Yeah, that's fine. There's only one angle B. I can do that. So angle bow. Look at that bow. Eat that bow. Anyways, measure of angle BAO. BAO, this one right here. So if that segment and that segment are congruent, and they are, right, because these are both radii, this angle of this triangle is congruent to that angle of that triangle. What's the reason for that again? Well, these two sides of a triangle are congruent, angles opposite those sides are congruent, and that is the ITT, the isosceles triangle theorem. Yeah, it comes back to us here. One of the most used theorems in this textbook. Okay, got two sides of a triangle congruent, mark of those angles. And say ITT. That's the reason why you know that they're congruent, okay? That's helpful to us because, check it out, I'm going to talk about measure of angle bow, measure of angle BAO, and measure of angle B in the next statement that I have here. Let's see if we can crack the code on this one. What am I saying? It's going to go kind of, you're the one who signed up for watching this video, so you're the one thinking hard about this. I'm going to go faster than you would do it, though, obviously, here. Measure of angle BAO plus measure of angle B equals measure of angle 1. Justification, why? Well, this triangle has how many degrees inside of it? 180. Angle 1 plus this, the vertex angle of the isosceles triangle, angle 1 plus measure of angle AOB would equal what? 180. Okay, 180. So angle 1 plus this equals 180. This plus this also equals 180. So remember, these are remote so this is an interior angle. It's supplementary to angle 1. These are the remote interior angles of this exterior angle, the exterior angle. So there it is. Number 4 is the exterior angle theorem, right? Exterior angle theorem. And the exterior angle theorem is great for this one here because check it out. We're comparing measure of angle B, right? Measure of angle ABC to the central angle, which is going to measure freaking minor arc AC right there. Okay, so that's good. But wait, in step 3, we said that measure of angle B also equaled measure of angle BAO. So you know what? What can we do? We can substitute measure of angle B. We can take this. It equals measure of angle bow, right? And replace measure of angle bow with measure of angle B. That's called the substitution property of equality. So we can put that in there, and that's good because it looks like 2 times, right? 2 times the measure of angle B equals measure of angle 1. That means this times 2 equals that. I think we're going to get to it sooner rather than later that this times 2 would equal the measure of that arc because it got measured by angle 1. And therefore, if this is twice as big as that, then this is going to be half as big as that, right? That's how it goes. You're either times 2 or 1/2, depending on the direction you go. So let's get the rest of the steps down here because, again, right, if you're writing a textbook, if you're writing something really sophisticated where, sure, you can explain the logic, but how do you do it clearly in this kind of this organized way? That's the accepted way to do a 2-column proof, for instance. Well, we keep working. We keep grooming it. We would say this next, right? And this would simply be, well, we combine like terms here. 2 times measure of angle B equals measure of angle 1. We don't need a step like that. We simply can divide both sides by 2. 2 times measure of angle B equals measure of angle 1. Well, divide by 2. All of a sudden, we'd have measure of angle B on the left side, right? We had two of them to begin with. Now we have 1. Divide the right side by 2. We'd have 1/2. Measure of angle 1 there. So that is the division property of equality there. And now we have 1/2 measure of angle 1. What do we know that measure of angle 1 equals? We haven't even talked about that yet in the proof. Measure of angle 1 equals measure of arc AC. Yes. That's why we put this auxiliary set in right here, is because we wanted to talk about that central angle. Yeah, we wanted to know how the central angle compares to this, because then we can compare this to angle B, and it's all going to connect, man, all going to get there. So here, step 7, why do I know this? Well, the justification of the proof, measure of arc AC equals measure of angle 1. Well, that's just because the measure of arcs, right, measure of minor arcs, are defined as the measures of their central angles is equal to the measure of central angles. So what you can say in the proof is just simply definition of the measure of a minor arc, okay? It equals the measure of the central angle. That's where it all came from. That's why we sort of said that this is how arcs work, right? Because it's a freaking definition. So remember, you can use that in a proof, right? If it says equals in the definition, you probably can use it to set up equations that you know would have to be true. It's probably the definition there, and it is here in this instance. Okay, So now I got measure of arc AC equals measure of angle 1. You see why this is like a rough class for me to do normally in a normal year. I'm trying to go through this thing. Oh, it's great. People falling asleep, people losing it. Gotta go to the bathroom, all that good stuff. All right, anyways, now I got this. Let's see here. Don't need to belabor this anymore. We can get, well, we got measure of arc AC. That's what I'm trying to get here. But I also have measure of angle 1. 1/2 times measure of angle 1. What do I got to do? I simply got to take this measure of arc AC and replace what it's equal to, measure of angle 1 up here in step 6. And there we go. We finished the proof. We finished this proof for what, though? Just for case 1, okay? So we get here, measure of arc AC, replace that, and check it out here. Look, measure of angle B. Well, that's the same angle as measure of angle ABC, like the same angle we're talking about here. So we've done it. We've proven it. We've done it here. But we've only done it, right? We've only done it for case 1. That's it, okay? So remember, the theorem that you guys have in the textbook is the measure of an inscribed angle is equal to half the measure of its intercepted arc. The theorem doesn't say anything about a specific situation like this, where that chord, one of the chords on the inscribed angle passes through the center of the circle, okay? The theorem goes more general about that. It says if you have any inscribed angle, you can rely upon this. This is a fact. It can't be argued with. And the reason is because it was proven. It's proven. We got to prove. It's proven in more ways here. So what we have here in case 2 up here, yeah, this guy right here, this gal right here, I don't know. It's more general here. Ooh, I'm running out of battery. Better make this quick here. Step 1, we're going to do it. We're going to introduce the case that would make this kind of like case 1. So we're drawing a diameter here, right? Inscribed angles doesn't necessarily have to contain that diameter. In this case, again, the center is in the interior of the inscribed angle that we're trying to prove. Still has to be 1/2 the measure of minor arc AC right here. So we're going to introduce segment BZ, and that is a chord. It's a special chord. It goes through the diameter, right? Goes through the center of circle O, because between 2 points, exactly one line can be drawn. So through point B, point O, boom, we can draw that line segment, ends it at point Z. We're good to go. And we can justify that there would be a diameter there that would pass through B going through O. And now we can use case 1 in our proof here, because check it out here. I can say measure of angle ABZ equals 1/2 of measure of minor arc AZ. Where did I get that from? Where did I get it from? Well, that's an inscribed angle up here. We know it's going to be equal to 1/2 the measure of its intercepted arc, but that's actually the theorem we're trying to prove. Well, why am I able to use this in the theorem that I'm trying to prove? Well, that's because I proved it already for this specific case, where I have an inscribed angle and one of the chords is a diameter. So I'm going to use case 1 in this. What we just proved with one another, we can use in a proof of a more broad example of when we have an inscribed angle that doesn't contain the center on one of the chords here. So, or one of the chords isn't a diameter here. So we've done that for measure of angle ABZ, 1/2 of measure of arc AZ. What's the other one? What's the other one we want to be talking about here? Yeah, we want to talk about measure of angle ABC at the end of the day. So we got to talk about this part of measure of angle ABC, which is going to be angle ZBC. And what we know about measure of angle ZBC, it's got to equal 1/2 of its intercepted arc, because again, look at that diameter. It's on both these freaking angles here. It's on this inscribed angle. It's on that inscribed angle. And we know from case 1 that that because it's a diameter and it's an inscribed angle, that's going to be 1/2 the measure of the arc here. Okay, so we're broadening this now. We've got it down. This is 1/2 of that. This is 1/2 of that. So what is the whole thing? It's going to be 1/2 of the whole thing. We just need to get the steps down, improve it, and here's where it gets a little messy, right? Here's where, if I'm asking you to write this stuff, you're just like, why am I doing this? I see it at this point. Why do I have to keep doing this? And let's keep doing here, because we have to have that idea of addition, I think, right? Part plus part equals whole, right? Measure of angle ABC plus measure of angle ZBC, for instance, equals measure of angle ABC, because part plus part equals whole. So we might as well say that next, which is, of course, what? Angle addition postulate, okay, coming all the way back from section 1.3 actually, the angle addition postulate. Oh, that's I got the R condition postulate. Never mind. We got the R condition postulate. So yeah, measure of arc AZ plus measure of arc ZC equals measure of arc AC, right? A minor arc AC there. We're good to go. And it didn't matter if it's a minor arc or major arc. It's going to work that way, right? R condition postulate works that way. So anyways, yeah, there we go. I got those parts. So anyways, that brings measure of arc AC into the proof. That's good. I just need to somehow change that to 1/2 of that at some point. So do I do that in the next step? No, I don't. I do the angle addition postulate. So again, part plus part equals whole. Here, part plus part equals whole. So part arc plus part arc equals whole arc. Part angle plus part angle equals the whole angle in terms of this measurement here. That's the angle addition postulate. There we go. So that's come back from section 1.3. All right, so now I have this. Now I need to kind of manicure this. I got to do some math moves to get my answer, right? To prove that my answer has to be true using the laws of mathematics. So we've talked about this here. Definitions, facts, rules, postulates, theorems, right? What can get me to justify this here? So I got measure of angle ABC. That's what I want in the proof, right? I also have this here. Look, I have measure of angle ABC. I want to get it to equal, not this plus this. I want to get it to 1/2 the measure of this arc here, AC here. So the problem is ABZ and ZBC, right? I have right here, neither of which is exactly equal to measure of arc AC, but they equal 1/2 of each of the parts here. So what I'm going to do in step 6 is I'm simply going to, well, actually first up here, I'm going to change this statement right here, because maybe this is where my big finisher is going to be, at least the way that I'm writing this proof here. So I'm actually taking this and I'm multiplying everything by 1/2 or dividing everything by 2. So that's going to be either the multiplication property of equality or division property of equality. Okay, so the reason why I'm doing this, so this proof is just written a little bit differently here, is I want to leave this one, I want to have 1/2 measure of arc AC in the proof. Now it looks like what I want to do is I want to show that 1/2 measure of arc AZ and 1/2 measure of arc ZC. Well, that's going to have to, if I add them together, that's going to have to represent measure of arc ABC. And it is, because look at this, compared to statement 5 to statement 6, they're pretty darn close. Measure of arc ABC. So anyways, like they're pretty darn close to be added together. Look, I have measure of arc ABC. That is measure of arc AZ. Here, measure of arc, of angle ZBC, that is 1/2 measure of arc ZC. So I can replace those two. So I'm guessing that's next, and it is. So I got measure of angle ABC plus measure of angle ZBC equals 1/2 measure of arc AC. Finally, what do we know about measure of angle ABC plus measure of angle ZBC? What is it equal to? What is it equal to? Look back in the proof. And step 5, if you're following closely at home, if you're keeping score at home, step 5 is what you're going to do next. Well, we did substitution earlier. I got to say steps 2 and 3. Yeah, we took what these two things are equal to and substituted them in here, right? This is equal to that. We replace this. Got us ABC there. ZBC is equal to that. Replace that. Got ZBC there. That was substitution. Last step is another substitution, right? We know that this plus this equals that, so we can replace these two things with what their sum is equal to, which is measure of angle ABC, and that gets us down to the end of the proof there, and that's substitution as well. And hooray, have we done it, guys? Have we done it? The measure of inscribed angle, it's equal to 1/2 the measure of its intercept arc. Did we do it? Did we prove it for all cases? We're done here, right? We're done here, right? What do you guys think? So we're done here? Well, we've proven it for this case, right, where we have the diameter here, right? Angle ABZ is 1/2 the measure of its intercepted arc. Arc AC, 1/2 arc AZ. We've also proven it for if your inscribed angle, it kind of goes around the center. The center is in the interior of the angle. But does that describe all inscribed angles? Any way I can draw it. So if I have an inscribed angle, it either like one of the chords has to go through the center as in its a diameter, one of the chords, or I have an inscribed angle. It could also potentially have the center in the interior of the angle. Does that describe the set of all inscribed angles? Because notice here, right, the theorem says that the measure of an inscribed angle, any inscribed angle, should be equal to 1/2 the measure of its intercepted arc. So we got to think, have we proved all cases? Or have we proved stuff generic enough that we can apply this rule to any inscribed angle? And it turns out, of course, there's one more situation we need to look at, right? We're wrong. You're wrong. We're not actually done with this yet, okay? So I'm shaking my head. You're getting pointed at because you're pretty good. You're pretty good at getting through these first two proofs, but now you're getting pointed off because you thought we were done. We are not done. What do we have? That's right. We have the third case, okay? Case 2, it went around the center. Case 3, look at that, inscribed angle. It's, of course, inscribed angles don't need to either pass through the center with one of the chords, or the center doesn't need to be in the interior of the inscribed angle. Because remember, an inscribed angle is simply defined as an angle whose vertex is on the circle and two sides contain chords. This fits the definition of an inscribed angle here. The vertex is on the circle, and both sides contain two chords. So if we prove it for this one, wonderful. We have it for all cases related to any type of inscribed angle, because either the chords, neither of which will pass through the center, and the center will either be in the interior or it'll be on the exterior of the circle. That's the case we're going to prove now. Or one of the chords will go through the diameter. So that's it, right? There's no other situation here. Okay, so this proof's going to work very similarly to the proof of case 2, because, well, what we're going to go back to, let's go back to case 1. Let's go ahead and draw in from point B. Let's draw a diameter. Draw that freaking diameter in there. And yes, we will, through 2 lines. Through 2 points. Exactly 1 line can be drawn. And what can we say? We can say, for instance, that measure of angle ABZ, this large guy right here. So let's take that. Let's take the largest that has this chord we introduced that goes through the center, so diameter here. So the largest one here, and say, well, this is 1/2 measure of arc AZ. Right, mark AZ. So that's simply from case 1 of this proof. We proved it for a subset of inscribed angles, and we're using that what we've already proved for this particular kind of inscribed angle to get us more general to all the other kinds here. All right, so we have that here. We can also say that by these 2 smaller angles right here, right? You can't say about this one, but we can say it about this one here. We can say CBZ, which I think we go there. Yeah, CBZ is the same thing as ZBC. Measure of angle ZBC equals 1/2 measure of arc CZ or ZC. And we're good to go there, case 1. Okay, and how's that important? Well, we wanted to prove it for the angle, the inscribed angle that the center is on the exterior, right? We're trying to prove it for this one here. Measure of angle ABC, we want to still say is equal to 1/2 of measure of arc AC. So we have those two together. We're going to work with R Condition Postulate, Angle Addition Postulate as well too, to kind of get this proven on out. First thing we're going to do here is we're going to do the R Condition Postulate. Well, I'm talking about AZ, I'm talking about ZC, and I care about AC. Right? I care about AC. That's things in my proof. And I know that AC plus CZ, arc AC, the measure of that arc, measure of arc CZ would equal measure of arc AZ. Part plus part equals whole. So I can get the arc addition postulate going for me. I can also get, again, the angle addition postulate, and I've highlighted some things out there to make things jump out a little bit more. Measure of angle ABC, so this part plus that part, equals the whole angle as well. We've been doing that a long time here, right? Measure of angle ABC plus measure of angle ZBC equals measure of angle ABC, and that is the angle addition postulate. Okay, this is important because check it out. I highlighted this in red earlier here. We want to get measure of angle ABC into the proof. We want to somehow marry that to measure of arc AC. How are we going to sort of manipulate things here? Well, we got some statements of equality up top here. So there's a whole bunch of substitution equation moving around. Try to follow my logic for it, but just the key is I want you to see that these are like really 3 cases we need to prove. And if you agree with me, agree with me. We move on with our lives. We take it as theorem, right? That any inscribed angle is intercepted arc is 1/2 of the measure. It's to double the measure of the inscribed angle. So the inscribed angle is 1/2 the intercepted arc. Anyways, let's keep moving on. What are we going to next? Let's see if we can see if you beat me to it, because I even forget what I wrote here. I wrote this one last year. Let's see here. So I got ZBC. Well, ZBC we already talked about up here. It equals 1/2 measure of arc ZC. So I might replace that. I'm sort of guiding to here. I might use substitution to replace that with 1/2 measure of arc ZC. I might replace measure of angle ABZ with 1/2 measure of arc AZ, and that's what the next step is, which is substitution, okay? And we're moving fast, we're going through, because what can I do next? Well, in this equation up here, I need to isolate measure of angle ABC. I need to get it by itself next to the equal sign. So perhaps I'm doing subtraction property of equality. I don't know if that's next, but it's sort of leading me that direction. Sure, that's it, subtraction property of equality. And let's see something else here that I could potentially prove in my 8th step, which is going to be measure of arc AZ minus ZC. Okay, and I want to get to measure of arc AC, so I might have to mess with this one a little bit here. Oh, what do we notice here? What do we notice about step 4? What can we do to step 4? Well, we can subtract measure of arc ZC from both sides of that equation. Okay, so just picture, look at step 4 real quick with me, because that's where I'm looking. That's where my brain's going. Step 4. I could have measure of arc AC equal to, so instead of plus measure of arc ZC here, I can have it equal to measure of arc AZ minus measure of arc ZC. And that's what we have there, right? That's what we have there. So remember, we got here differently, right? We got here from the angle addition postulate and then substitution, and then we subtracted, and we got it set up like this. I can also change this statement here, statement 4, by simply subtracting measure of arc ZC, which is got to be, I'm doing 2 things at once here. I subtracted measure of arc ZC, moved it to the right side, and I needed to save some space. So, right, so notice here, and then I multiply both by a half, right? Both sides of step 4 by a half. And what do we notice? Well, this expression here is the same expression in the equation in step 7. So what can I do to finish this? Well, let's look at the left sides here. This thing equals that thing. That thing also equals this other thing. So you got this thing equals, first thing equal to a second thing. I'm talking about that whole expression there. And the second thing, the whole expression, is equal to a third thing. What do the first and third things equal? They equal each other. When you have 2 things that are each equal to the same thing, they are equal to each other. That's the transitive property, right? It's been said for thousands of years. Euclid wrote it in the Elements, and Lincoln cited it in terms of arguments for emancipation of enslaved people. It's pretty big there. And did I write transitive? I wrote substitution. After all that, substitution. But hey, we got it done. Hey, so you there? You there with me? Are you like at this right now? Because that's the longest proof in the book of any theorem that at least I go over with classes year in and year out. So no is optional. Hope you're just not like, what the heck was that? We're done with this. But anyways, thank you for watching here, giving you some more perspective on how some of this stuff works, kind of the machinery, and really getting down and dirty. If you want to figure out how things work, I appreciate going through this effort to watching this video, trying to figure out exactly how this proof works. Sometimes you need to prove it for several cases to capture everything, so you know it's true about any of those types of shapes. Thank you for watching. Message me if you have any questions. Take care. Bye.